All right, so just a quick recap from last time. No need to scroll up there, but we were essentially looking at different algorithms that had various time complexities: constant, logarithmic, linear, polylogarithmic, polynomial, and exponential. So we've encountered a lot of these. We haven't encountered a polylogarithmic algorithm yet. We'll look at that when we get into sorting. And we haven't done any examples about exponential algorithms yet. But exponential algorithms are just going to blow up in your face very quickly. And of course, something that kind of blows up in your face when you were in discrete was the power set. So I encourage you maybe to play with a power set a little bit over the weekend, just to kind of get that in your mind. But of course, the power set of, let's just say, a discrete set. Let's not talk about like the power set of real numbers like we were chatting before class, and just do some sort of countable set right here, or I shouldn't even say countable, but a finite set, that's the word. So the set of all subsets of a set. So of course we generated the power set 4, 1, 2. It had 4 elements, and we talked about the cardinality of the power set of a list. This is going to be of size 2 to the n, where n is the size of the list. So let's go ahead and generate, just as a quick little warm-up, the power set for the list 1, 2, 3, or the set 1, 2, 3. And kind of when we kind of write this in Python, we'll just use a list to kind of represent our set. There is a set data structure, but we really didn't talk about it. So, of course, every set has a subset that is the null set. So let's see, we have then the sets 1. Then we have the set just containing 2, and then we have the set containing 3. Then we have the set containing 1 and 2. Then we have the set containing 1 and 3. Then we have the set containing 2 and 3. Boy, this is a fun little typing exercise. And then last we have the set, what am I missing? Just 1, 2, 3, right? Is that the only, do I have 8? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's a good enough example for maybe what we're going to reason about. And again, this you can see that the number of elements in the set are going to grow, basically. This, of course, has 8. Then this is how many sets will be in the power set of 1, 2, 3, 4? Or how, yeah, say again? 16. So there's just that exponential nature of generating all of them in the power set. So how do we do that? So let's suppose you were to write a program to generate the power set given a list. And again, just think about it. How would you do that for a moment? Maybe just pair up with 1 or 2 next to you. Is there some property that you would maybe rely on to generate the power set of a list?
Property or
just talk through it a sec. What would be a kind of a general algorithm? And try not, I mean, you can look down below, but it might be a little bit hard to decipher. But think about, like, what would be a good way, or an efficient way to generate this? Oh, I needed to pull something. All right, let's go ahead and come back together and discuss it and see what ideas y'all came up with. So again, I have, of course, an idea, but what ideas did you guys kind of just throw out? Alejandro, what do you think?
A range within a range function.
A range within a range function. Okay, so I like the idea of within a function. So do we have that idea in programming? We called it something. Function within a function. So is nesting. Okay, what else? What other ideas are there? Okay, we'll probably need some for loop to iterate through them. Okay. Any other ideas? I think it's always fun just to think about how you do it, and I would always encourage you to maybe, as you encounter problems, just maybe talk them through, see what ideas you come. But there's a clever idea that is I see to generate this. So here's the basic idea. Let's make it concrete. So if you look at these right here, we start with nothing. That's kind of nice. But as we build it, here, so we're going to essentially build it in a different way than I built this set right up here. So realize that, again, the sets can be reordered. This is just a property of sets. So like, I don't necessarily need to generate the null set first, then 1, then 2, then the 3, then 1, then 1, 3. I don't need to do it in that order. That's just a property of sets. So keep that in mind. So what we're going to basically do in one sentence is to generate the power set of integers from 1 to n. Assume we can generate the power set of integers from 1 to n minus 1. What does that statement feel like? Okay, so it relies on the previous one. Anna, this should be standing out to you based off of your project.
Mathematical induction.
Induction. So again, if we're not going to talk about in this course about how to prove that algorithms are correct, you rely on certain proof techniques that you've encountered before. So again, this right here should feel like mathematical induction. Let's go ahead and assume that we can generate everything up to n minus 1. We'll just assume kind of that our elements are 1 to n. And then we'll use that assumption to go ahead and create the next few elements. So to generate the power set of 1, 2, 3 as above, essentially what we'll do is let's go ahead and start with the empty set. Start with the empty set. So our power set will start with just null, the null set. And then what we're going to do is we're then going to include the previous sets. So we're going to include 0, or the null set. Okay, but we're also going to include and 1 included in each subset. Let me give you more space. So we started with the empty set. Let's include n plus 1. So if we started with n equals 0, let's include n plus 1 there. Or you could phrase this, if we started with n, let's assume we could create n minus 1, and then to go ahead and create the sets of size, let me say that again. The next set, like with element n, we'll just go ahead and take what we had and add 1 to it. All right. So that takes care of a couple. Now what we're going to do is include the previous and 2 included in each subset. So let's take the null set and 1. Those are already there. And include, I'll just do this on the next line, let's include 2 with the null set, and let's include 2 the 1. So we are just building one more element with the previous subsets we've created. Okay, and then what are the last ones we're going to generate? So finally, we're just going to include the previous subsets and 3 included in each subset. So we have 0, the null set. We have the set with 1. We have the set with 2. We have the set with 1 and 2. And what are we going to generate? What is the next subset we're going to generate in the power set? This is the set containing 3. Then the set containing 1 and 3. Then the set containing 2 and 3. And then lastly, I guess if I lined these up a little bit, let's line that up there. There's 2 and 3. Then lastly, the set 1, 2, and 3. So we generate them a little bit differently here, where we're not necessarily doing all the sets of order 1, all the sets of order 2, and all the sets of order 3. We're basically just adding one more element one more time through the iteration each one. So that's the basic idea of this algorithm right here. So let's just kind of look at this algorithm. Let's get it all on one page right here. But if you look at this right here, gen subsets, and one thing I could go ahead and mention, you could always convert a recursive algorithm to an iterative algorithm. I just had to do that for my last homework problem because recursion is a pain in the butt sometimes. But it does really kind of make things a lot easier to keep track of right here. So you can see gen subsets is going to generate the power set. So you could also call this gen power set. This is just the code I worked with here. So if the length is 0, this is the base case. You're just going to return the null set. But if you are going to need the next element, you look at what this says right here. You're going to essentially grab the last element off of L, and then you're going to create that right here. So here's the recursive step right here. And then you look at the extra. So you're going to create a list of just the last element. So, no, let's do it this way. Let's go ahead and step through it using an actual example. Let me go ahead and call this. So let's generate the power set of order 2. I think it'll be easier to see it actually in elements than just looking through the pseudocode. All right, so let me go ahead and put a breakpoint. And where's the other breakpoint? Let's go ahead and run. All right. So we're going to generate the power set of size 2. And what let's step through this. The first thing that you're going to see is that the list is not of length 0. So you're going to go down here and you're going to essentially pass in a smaller set. So you're going to remember this notation right here is going to say 0 to the last element. And of course, remember it's not inclusive, so it's going to chop off the last element. So let's see what happens. We are now going to go one more. We're going back to the top, but we're now one more level lower in our call stack. And you can see right here, the list in this one is just one. So there's the call stack down here. You have the outer function, then you're now in the recursive step. And you can see right there, it wasn't length 0. So we're going to now step into one more. And now you can see the list is 0. So this is where we're going to first generate the null set. So you can see right here, it's going to return the null set. We come back out, and smaller, let's go ahead and it'll now define the next step, is what is just the null set. So you can see right here, this was the first one. Yeah, Kenneth.
I'm a little confused how the length of L was changing if we were defining something new as smaller.
So smaller right here, this is a recursive function, so you're passing in. So the first time you call it, you're going to pass in to the function, we'll just say f of 1, 2. So this is the first one. And then the first thing you're going to do is check if it's the null set. It's not. So what you're going to do is essentially call it with everything but the last element. And then, again, this is not the null set. So now you're going to go ahead and call it with the null set and a list of length 0. And it is now going to return, this is going to return the empty set, the null set. So you can see it now stored that in smaller. So this is, again, like we now have our first element of our power set. It's just this right here. So extra, let's go ahead and just see what extra is. So extra is going to be 1. So it's just going to, because right now it's right here. It's just looking at this list. It's not in the initial call. It's in this one. So it's going to grab the last element from this one, and it's going to create just basically an extra array that you're going to append onto it. Because again, power set is a set of sets. So this new is basically the power set you're building. So let's see what the next step is. So for small and smaller, which is, of course, the one that you got from the step down in the recursive call, is going to now going to append to new. And here's the thing to remember with addition of lists, you concatenate. So you can see the first thing it's going to do is so the power set's still there, but it's going to append to the power set the last element. So you can look there, we have smaller is the power set, and now here's the new one. So now we're going to append smaller, which was just the empty set, and then we're going to go ahead and append to smaller the new, which just has that 1 in it. So you can see right here, let's see what we got. Actually it went out, and it's now going to put 0 and 1 in smaller, and it's going to go ahead and repeat. So let's see, you can see that right there. And now it's going to go through that same logic. It's going to append the null set in 1, and that 1 is going to be obtained from the, or let's see. So for small and smaller, so right here you can see it. So smaller contains the null set and the set containing just 1. And then you'll go ahead and for small, so just you're going to go through these 2 right here, and you're going to append 2 to each of them. So there's that one. So this is the other 2 for the power set, and 1 more. You're going to now append 2 to 1. So there's that one, and then these 2 will be added to the power set, which will be returned out here. And then you could go ahead and print it, and you have the power set right there. A little bit of a tedious algorithm to work through, and I kind of went through it fairly quick. So the main thing I want to call out about it, let's maybe just focus on that right there, is these few ideas down here. Each recursive step has a longer, smaller list to generate. So the first time it just had to generate the power set, or the null set, so that's 1. And then it had to generate the power set, and then it appended to each of those just 1 more element. So if you think about what is happening here, each recursive step is where the algorithmic complexity is increasing, and is increasing by this exponential growth. Say again?
You're going to show us how the exponential program.
Yes. So basically, within some sort of recursion or within some sort of loop, you're doing twice as much work each time. Or you're doing some sort of, again, it doesn't necessarily have to be base 2, although that's the most common one. You're basically increasing the work by a power of some base or some number. So this is just a type of algorithm I wanted to expose you to, whereas algorithmic complexity is 2 to the n, where n is the length of the list. So something where each step doubles the amount of work. So that's this. So you won't have, of course, to do something this intricate on a test or something, but I just am trying to expose you to some different types of algorithms. So spend some time with it, maybe play with it yourself, step through it, just your own time, just to be more comfortable with where the complexity explodes, which is in basically this step right here. Okay, so that's one type of exponential. Another one is Fibonacci. So if you recall back way to the beginning of the class when we were really talking about Fibonacci, it has this structure right here. If you look at this, look at each step. Let's see if I don't think right here. Let me try something. Let me copy this, insert, drawing, new, paste that. Does this work? And zoom in. Yeah, it might work. So if you look at the numbers as we do the recursive calls for Fibonacci, let's see. Is that big enough for you all to see? Yeah. Okay. And scribble, look right here. There's one call. It's not working like I thought it would. Maybe I can't draw in the image. Sorry. This is a disaster today. No, now it draws. So again, there's 1, then you can see there's 2, then there's 4, and each step we're doubling the amount of work from our previous step. So of course we did realize there were some tricks to shorten this algorithm, and to reduce the amount of calls. And does anyone remember what that process was called? Anyone, just throw it out there. Memoization. So you can see right here, this is another scenario where you have an exponential algorithm. So 2 to the n, where n is again the input here, not necessarily the length of the list. All right, so let's summarize constant functions. Or not constant functions, but algorithms that have constant time are basically the code does not depend on the size of the problem. So any sort of algorithm that's basically just additions or subtractions or multiplications, basic operations, these are your constant algorithms. There's very few of them, and that's unfortunate, but that's just how life is. When things get bigger, things get harder. But there are some constant type algorithms, such as just looking up something, looking up a list access or something like that. Log n. So does anyone remember what type of algorithm was characterized by a logarithmic time complexity? It's when the problem is cut in half. So basically, if we can reduce the problem size each step, and of course we looked at an example last time being binary search. We essentially took half the list, threw it out, because we knew that it was of course sorted, so we didn't necessarily have to worry about half of the list each iteration through. So in general, any sort of algorithm that is going to reduce the problem in half, so the problem is reduced in half each time. This, of course, is a type of class of algorithms called divide and conquer. So then we look at algorithms that were big O of n in time complexity. What was this algorithm typically just doing? It's just a loop, something repeated n times. So this is basically some sort of simple iterative algorithm, and sometimes even recursive, and also simple recursive algorithms. So something where the work doesn't blow up like it did in the generation of the power set. N log n actually have certain, so you'll see n log n in popular sorting algorithms. And we're going to realize, and this is something to think about as we progress in today, that could you ever do something better than n log n? Or what is like the lower bound on the runtime for sorting algorithms? So that's something we'll talk about more today. And of course, when we looked at polynomial type algorithms, so like n to the c, these of course were like nested loops were involved with polynomial time algorithms. And most commonly you'll see exponential in recursive algorithms where the work increases each step. Or instead of step, I should say each recursive call. So basically, that's the next step down the tree. So Fibonacci, or the generation of the power sets. So we've looked at a couple of examples of each of those, with the exception we haven't done anything with n log n. So let's go ahead and switch over to sorting. Any last minute questions on video? Yeah.
This is probably a dumb question. But,
Ask away.
Is there a possibility of getting something better than a constant time, like something where the time would decrease with a bigger sample size, like 1 over n? for example?
Size would decrease. Well, that's what you're kind of getting with a logarithm, is that each step cuts the problem in half. So.
But it would still take more time in general. Like, yeah, I guess.
So you are describing like worst case. So, and again, this is in terms of, remember big O relates asymptotic complexity. So it's talking about the problem size increasing. How does that affect the running time? So like you're thinking like, is there a problem where the problem size increases, but
Like, is constant the best thing you can
Yeah.
Okay.
Basically, like, it's going to take the same amount of time every time. It's not like when you increase the problem size is going to increase the length of time needed to do the computation. So, like, if you increase the problem size and it were to take, let's say, 2 units of time, if you quadrupled the problem size, it will still take 2 units of time.
But there's nothing where you quadruple the problem size and then it takes 1 unit of time.
I don't think so. If you start with a problem size of if you start with just thoughts. So if you start with a problem size of what? Let's say 10 units, and it takes 10 seconds, but then you reduce the problem size to, let's say, 2 and 20, and it takes 5 seconds, something like that. I have to think about it. My gut says no, because you have to at least, unless if you change the problem.
I was curious about like a machine learning maybe or something.
So machine learning typically is going to do machine learning comes down to training and then testing. So like you're going to train on something that takes a long time, but you would test on a different piece of data, and obviously it's going to take smaller because you're just asking it to make a decision on the testing data. So I don't know. Let me think about it a little bit more. Maybe formalize this problem a little bit. But there are certain restrictions on, like, you're going to always have to do at least a minimum amount of work, or you have to at least do. I'll make it concrete in the next one. I'm trying to do too much in my head. Okay, so let's talk about sorting algorithms. So sorting algorithms, we're going to run into that case where you're going to have to do something regardless of what algorithm it is, and it's going to basically put a lower bound on the best, or it's going to put a lower bound on the best case. You're going to always need to at least do something in a certain amount of time. So last 5 seconds ago, we were discussing searching algorithms. So we have these 2 algorithms right here. So the search one right here, what type of search are we looking at where we send a flag equal to false, and then we iterate up to the length of L, and if we find some element E, we set the flag to true, and then when we're all done looping, we go ahead and just return true or false based off whether we found it. What type of search was this called? We had to go through all of the list, so therefore it starts with an L, ends with an ear, and we got in the middle. So it's a linear search. If you look at the structure of this, it's going to go through every single element of the list, and it's going to check if it's the element that we're looking for. This search works on an unsorted list. So we slightly modify it, essentially to use this right here. We're going to make an assumption that L is sorted. So the second search, if you look at it, is we're iterating through every element in the list. So what type of search is this? Still linear. Was a trick question. But the second one is relying on some property about the list to return early. And it's relying on the fact that L is sorted. So let's think about, what is the worst case for either of these algorithms? We talked about this, I think, a time or two ago. What is the worst case? Just Seth. So it's not in the list. So the worst case is not in the list. So what does that mean? We had to essentially search through the whole list. Not in the list is the worst case. So we had to search the whole list. What was the worst case time complexity? It was linear, so it is big O of n. Now, this is something that we, I think, mentioned. What is the best case for these algorithms? Caroline? It's the first element. So the best case right here is the element E is the first element in the list. So what is the best case time complexity? So if the list was 10 elements or 1,000 elements or 1,000,000,000 elements, if you knew it was the best case, is it going to change the time? If you always, when the first element you check is the one that you're looking for, is that going to change the time? It's not. So whether the list, let's say if it was the list of the first 100 integers, 1,000 integers, or 1,000,000 integers, and you were searching for one, is it going to take? It's going to take the same amount of time because it's going to find it first, right? So what is the time complexity in the best case? Constant. And what we'll go ahead and do is introduce a new type of notation to describe the best case, and we'll typically just use this notation right here, and that is the Greek letter. Does anyone know their Greek?
Omega.
That is big omega. So what we have right here, and because you don't have an omega on your keyboard, I am just going to copy and paste. So the best case right here are these algorithms are big omega of 1. They're big O of n, but they're big omega of 1. Okay. So blank search, and again, that was just to not spoil it from earlier, but linear search took big O of n steps, but the list needed to be sorted. On this, where was I going with this? Okay, so linear search took big N of n steps. So did we have a better search algorithm? That's where I wanted to go with this line. What was our better search algorithm? It wasn't linear, but it was, starts with bi, ends with airy, binary. So does anyone remember what the time complexity for a binary search was? It was log n. It cut the problem in half each time by just ignoring each side. And again, the caveat was the list needed to be sorted, because you did rely on the fact that that if you looked and you saw, let's just say right here, if you were looking from 1, 2, 3, 4, 5, 6, 7, and you were looking for 2 and you saw 4, all you just did was crossed out the right side of the list. That essentially was binary search. But so it did rely on the fact that the list was sorted. So we want to talk about sorting. What if the list is not sorted and I wanted to do a binary search? It was a lot better. It was log n compared to n. So how much additional work will it need to take, or how much additional work will it take to sort the list? That's a rhetorical question. We're going to answer that over this next few sections. So sorting. We want to efficiently sort a list of numbers or a list of entries, typically numbers, and there are several ways to do so. So just to expose you to a couple of them up front, let's watch this video. So let's open this preview. Hold on. I should have checked the sound before class. You're going to love the soundtrack that comes with these. So let's do, where's my speakers? Crestron, MacBook, Crestron. Okay, there we go. So here's another way to sort. Basically, is sorting them by height. This right here is known as insertion sort. And by the way, the sound effects is just playing the frequency as it accesses the element. So you can see as it accesses higher elements, it's playing a larger element is playing a higher frequency. Hence, it just climbs up there at the end. So this right here is known as quick sort. But notice there's different ways to sort it, and just kind of start paying attention to different little patterns. We're down here at the low ones. Quick sort is actually quite quick. It's using LR, which are left and right pointers. So you can see there's kind of a left and right of each part. let's see, the next one right here is merge sort. So pay attention to this one. Why do you think it's called merge sort? So if you look at this, this is a type of divide and conquer algorithm. So that's just to expose you to a couple. This one right here is heap sort. This is a parallel algorithm because you can see us doing different sortings of different parts at the same time. So that's kind of fun. And what's really impressive, here, let this one finish. These are just 15 sorting out. We're not going to do 15. We're going to do 3. All right. So there's a radix sort. And this is the best right here. Let me find it. Is it right here? Where's the pun? Anyway. Oh, there was a pun basically. Anyway, they listened to that because they wanted to listen to all sorts of music. Okay, yep, it was bad. It was not my pun. But all right, so let's go ahead and actually learn about a couple of these. So the one thing to keep in mind, what is the worst case scenario when sorting? So let's think about this, the same as before. You have a list of elements. What's the worst case scenario?
No two are next to each other.
No two are next to each other. It gets worse than that. No two. So let's think if you had 1, 2, 3, 4, 5, 6, 7, you needed to sort them. What is completely unsorted? 7 needs to go to the front. 6 would need to go here. Okay, these are sorted, so. Sorry. So I meant to be in this way. 7, 6, 5, 4, 3, 2, 1. 7 would need to get all the way over there, and 1 would need to come all the way over here. 6 all the way, 2 over here. 5, then 3. So what do you know? The worst case scenario, the order is reversed. Everything needs to move everything would need to move. And it has to move far in a lot of cases. So the worst case scenario is that the list is reversed. So if you were asked to sort a list of numbers, what is the best case scenario? It's already sorted. It's already sorted. So at least how many operations are necessary in the best case? It would be linear. Why?
You have to check to see if each one's.
Because you have to check. So no sorting algorithm will be better than linear, because you're going to at least have to check that you have a sorted list. So to put that in words, linear number of operations, because we need to verify the list is sorted. So there is a kind of a lower bound. A best case is going to be linear. Okay. So let's look at a couple different algorithms. The next project, how are we on time? Okay. So we are going to look at 4 algorithms, and this is what I think might be the best way to do it. Is anyone going to go to the baseball game on Wednesday? Caroline and I are probably going to go. So Caroline's going to enjoy it. I'm going for mandatory fun and a hot dog. You can get me anywhere with food. No, it's going to be fun. I've gone the last few years. So if you guys don't mind, what I would like to do is go through maybe 1 or 2 of these together. Then I could go ahead and record the video on the other ones for you to watch sometime this week. And then on Friday, I would like to have it to be a lab day. The next project, I'm still finalizing it. I should have it finalized by tomorrow. I'm going to essentially give you 4 programs that sort a list, and you're going to have to look at how long each of them take, and you're going to have to tell me which sorting algorithm I used. So you're going to basically be given some test data. So just maybe expose it to you a little bit. So just to kind of let you know what's going on this week. Hold on, let me pull up the actual project to kind of put it in your mind. So let's do this. Project 5 is sorting. So what you're going to look at, you can see I have 3 sorting programs. I'm working on one more I want to put here to try to get 25 points each. And I'm going to give you a bunch of data. So like right here, just a random 10,000 integers sorted random and are just thrown random, and you want to call a sorting algorithm. So what you'll do is you'll just go ahead and run it and you'll time it. So you would do like time and let's say sort 1, and then let's go ahead and have it pass in random 10,000.text. It's going to go ahead and sort them, and it's going to tell you how long it took. And then let's go ahead and do that same thing, but let's do random 10,000, but let's this time do sort 2. I did sort 1 again. I meant sort 2. And then let's see, that was 0.82. Let's do sort 2. This one seems to be doing a little bit better. You may want to average them out and play it out a couple times and see what happens. And then you can see I've also am giving you some reversed data where basically the numbers are reversed. Then I'm going to give you some sorted data, so the best case, worst case, and average case. And essentially your goal for this next project is just going to be telling me which algorithm are you using. It's going to either be, I'm working on one more right now. I don't want to spoil it, but it's going to be one of the ones that we're going to learn about in this lesson. So let's go ahead and take a few minutes, learn maybe the first 2. I'm going to go ahead and record the remaining parts, and then if you want to watch it on Wednesday, you're welcome to, but I'll leave class time on Friday. So Wednesday's like canceled, but I just want to make sure I expose you to the lists early enough. And again, if you don't get it to watch it until a little bit later, that's fine. And we'll probably have the project due early next week. This will be a shorter one because you're really just going to be analyzing and answering why, not actually coding. So does that sound like a plan for the week? Let's do 2 here, 2 in video, and then Wednesday no class, and Friday will just be a lab day where if you didn't get a chance to watch it, you're welcome to, or you could just work on the project. Does that sound like a plan?
Yes.
Okay. So the first sort that I want to make sure we're aware of is called BOGO sort, maybe short for bogus, but it's also sometimes called permutation sort or slow sort or stupid sort, which is not politically correct, so I didn't put that up there. But if you look at the Wikipedia, yes, it does it is referred to it as that. So the summary of how this sort works is you're basically going to shuffle until correct. It's bogus, right? So let's go ahead and just look at BOGO sort in action. So here it is. It is just shuffling, and it is just looking around until it gets something in the right spot. Okay, got a second element. So is this a very efficient algorithm? No, got a third element. Good job. So it does, it picks up its speed a little bit. So there's BOGO sort. You know that game, 52 pickup? 52 card pickup? If you guys played that game, that would be so mean. I would never do that to my sister. Anyway, imagine sorting a deck of cards using BOGO sort. How would you do that? You throw them into the air. You pick them up, and you check if they are sorted. And you basically repeat if not sorted. So there is, of course, BOGO sort. Not very efficient. So here is a quick little implementation of BOGO sort in Python. So you are shuffling, so we import from random shuffle. We have some basic function that will check if it is sorted. And this is kind of a fun little line of code. Just if you think about what it's doing, it's actually iterating through all elements and in the data, but skipping the first element. So it's pairing up like elements, and if it is always less than or equal to, the first element is always less than or equal to the second one, always, hence the all in front, it'll return true. But this is basically the algorithm. While you're not sorted, shuffle, and, well, once you are shuffled, you can go ahead and return the data because it'll be sorted. By the way, remember, lists pass by reference. So again, you technically did not need to return it. The data would have been modified. So it just was a safety thing right there. Okay, so worst case. How long is this algorithm going to take in the worst case? There is something worse than exponential.
Factorial.
Something worse than factorial. Huh? There's no bound here. If you're really unlucky, this could literally take you eternity. I mean, you just throw it back up. There's no probability distribution in this here. So worst case is unbounded. We don't even put big O in right here because, but what is the best case? First try. Okay, so if you were to sort, what is the running time? Best case, so big omega of, what did you say, Anna? N, because remember, you still have to check that it's sorted. So it's not constant, it's still going to depend on the length of the list. All right, so let's go ahead and do bubble sort. We may not have, I'll go through it. But basically, the idea of bubble sort is pretty intuitive. What you're going to do is repeatedly swap the adjacent elements if they are in the wrong order. Okay, so let's look at bubble sort in action with that in mind. So you're going to be comparing two elements next to each other, and you're going to swap them if they're in the wrong order. So let's go ahead and watch bubble sort for a sec. But notice how they're doing it in pairs. They're probably wondering over there, what are we listening to? But look right here. This smallest element is almost to the beginning. So notice now we no longer look at these smallest elements because they're already sorted. So you can see that now each time it's getting a little bit farther along. So making our way along. Oh, actually, it was this side that's sorted. Sorry, I had this backwards in my head. Okay. All right, there. We got to finish it, right? It's the low ones. So there's bubble sort. All right. Instead of doing I'll record a lot of this lesson. Let me show you. Let's just watch these last two videos, and then I'll leave the video to go through the details. Selection sort. Let me just summarize selection sort, and then But what selection sort is going to do is going to repeatedly select the minimum element from the unsorted part and put it at the beginning. So that is what selection sort is going to do. Repeatedly select the minimum element from the unsorted part and put it at the beginning. So let's watch this one briefly. They all sound so fun. So look here where it's flashing red. Is looking for the smallest element. It's going through all the lists and put it right there. It's in the right spot. So look, it's finding the smallest element. It's checking everything else to see if it finds something smaller, and it put it at the beginning. So that is selection sort. It's just looking for the smallest element, and it's putting it at the beginning. That's selection sort. You're also mesmerized by this. But notice this is speeding up.
Why is it speeding up?
Because we're relying that there's some invariant. The invariant is that up part of the list will be sorted. Satisfying.
That one didn't sound as nice.
It did not. Some of them have some very nice sounds to it. All right. And let me expose you to the last one. And the video will take care of a lot of the details. Merge sort. So what merge sort is going to do, it is a divide and conquer, got to spell correctly, algorithm that divides the input array into two halves, calls itself for the two halves, and then merges the two sorted halves. So think about that sentence, and then let's watch the merge sort happen. It's going to basically divide it into two arrays, and it's going to do that until, again, well, you'll see it. It's going to do it until basically, by the way, is a list of length 1 always sorted? Yes, a list of only one element is always sorted. So that's what this is going to be on. So you can see it's doing little pieces, and then it's going to merge those. It's going to sort basically size 1, size 2, size 4, size. So now it's going to merge these. It's going to merge these two because they're sorted. And it's to do the same thing over here. It's so fast. So these are sorted. Now these. And now it's going to sort these. It's going to merge these. It's going to merge. It's going to merge these. And then it's going to merge those. There's merge sort. All right. So I'll go in the details in a video. On Wednesday, no class. On Friday, we'll have a lab day, and then I'll get the details out for the homework probably by tomorrow at the latest. Does anyone have any questions on anything? All right. I hope this left you in all sorts of pain, but I don't know. It's the music. Have a good day, everyone.